Hi everyone, I will give you a short introduction to my project I have done at HKUST in 3 months. The objective of our project was to realize a multi-robot SLAM system. There are many possibilities how to set up a multi-robot SLAM system. However, a multi-robot SLAM system can usually be split up into two parts. One part is the slave robots, and the other part is the central computer. The slave robots usually move around, carry sensors, collect data, and may be very limited in computational power. The central computer usually has high computational power, can be stationary, or may not have any sensors. However, a multi-robot SLAM system can be set up in very different ways. The slave robots can also have high computational power, or the central computer may even not be part of the system when the robots are able to communicate among each other. The central computer may even be one of the slave robots, and so on. There are plenty of setups of multi-robot SLAM systems. Examples of slave robots can be mobile phones, aerial, water or robots moving on the ground, or everything you can imagine that is able to communicate with something else. Examples of the central computer are, for example, a server or any stationary computer in a room, or a high computational powered slave robot, or whatever you can imagine. The setup in our project, however, consists out of several slave robots with low computational power and equipped with a monocular camera only. Furthermore, there is a central computer with high computational power. In our system, the slave robots are not able to communicate with each other. Each slave robot only communicates with the central computer. We chose to do so because communication in a multi-agent system can be quite complex, and we did not want to focus on this. Our focus was more on fusion of different maps originating from different robots, based only on visual data originating from monocular cameras. Roughly speaking, the system works as follows. Each slave robot collects data from the monocular camera, rectifies the images, and runs a SLAM algorithm, estimating its current pose in its local coordinate system. After a slight processing of the collected and estimated data, every slave robot sends the processed data to the central computer. The central computer builds up a global map containing all local maps of all robots. To do so, the central computer runs a place recognition algorithm called FatMap in order to know where to stick the maps together. Furthermore, since the whole system is based on monocular cameras only, it is impossible to calculate or estimate the absolute scale of the maps. Therefore, each map has a different scale depending on the initialization of the corresponding slave robot. Hence, the computer estimates the scale differences between the different local maps to fuse the maps together and to build up the global map. It is important to note that since only images from a monocular camera are used, it is impossible to estimate the absolute scale of a map. That means it is impossible to know what distance in the constructed map corresponds to 1 meter in the real world. At the initialization of the SLAM algorithm, some arbitrary distance in the constructed map is set to the distance 1. This is different for each initialization. For example, if the slave robot starts very close to an object, the distance of 1 in the constructed map may correspond to, for example, 10 centimeters in the real world. However, for a robot initialized when the camera is facing to some mountains far away, the scale of 1 in the constructed map may correspond to 100 kilometers in the real world. That's why it is very important to estimate the scale differences between different local maps from different robots. So, I will show you now how to install and set up a system with one central computer and 2 slave robots. Instead of using real robots and a real central computer, all of them are simulated as ROS packages on my laptop. So, this installation tutorial is also described in the readmes of the slave robot and the central computer packages on the Git repositories on Bitbucket. So the first thing you will have to do is to install Linux. We use Linux Ubuntu 12.04, long time support. You can get it from here. Then you need to install ROS. We use ROS Hydro. And you need to install Git by typing this command into your terminal. Then you need to download the two ROS packages, Slave Robot and the Central Computer ROS package from Bitbucket. So you can get it from these links. It will look like this. To get it, you can use clone command and just copy and paste this into your terminal, and it will download the code of our project. You need to do this for both packages, the Slave Robot and the Central Computer. Then you have to put them into your Catkin workspace folder. If you don't have any Catkin workspace folder yet, Catkin workspace folder for ROS, you can easily create it with the following commands. You just have to copy and paste these commands into your terminal. That's what I have done here. Here's my Catkin workspace folder in my home directory, and I put them in the source. You have to put them in the source folder. So I have the CC, the Central Computer package, and 2 copies of the Slave Robot. So this is two times. I downloaded 2 times the package from the Bitbucket, the Git repository. Okay. Also, you have to download and install the LSD-SLAM from GitHub. It is there. The installation tutorial is described on the webpage. You can also put this into your Catkin workspace folder. As you can see here, in the source folder, there's the LSD-SLAM core and the viewer. You will get this from the repository, from the link, from this link here. Furthermore, you have to download and install OpenCV 2.4.9, OpenGV, the point cloud library PCL, and the eigen library for the linear algebra. The links for the downloads are also in the readmes of the Central Computer, and so you will find them in here, somewhere in these readmes, in the readme first probably. Exactly. So when you download all of them, you should be able in your Catkin workspace folder, you should be able to type catkin make, and it should compile without any errors like here. So you should be able to run your system now if this works like this. After having installed Linux, ROS, OpenCV and so on, your structure should look something like this. Somewhere you should have your Catkin workspace folder. For me, for example, it's in my home directory. In there you have the source folder where you have your ROS packages inside, and for me, for example, I put my bag files into my Catkin workspace folder, but that's not necessary to do so. So in the source folder you have all the ROS packages, for example the Slave Robot, and I copy and paste it such that I have 2 Slave Robots. Then the Central Computer with the irritating name CC FatMap, but it's a Central Computer, and the LSD-SLAM. Inside these ROS packages, you have for all of them you have the source code. So it's in the source folder. That's the source code of this program. The same for the Slave Robots. The source code, and such that you can see that it's just a copy. It's exactly the same inside Slave Robot 1 and Slave Robot 2. After setting up the system, you can run the system. To run the system, just open the run system readme.txt from the central computer package and copy and paste the lines into a terminal. So I go to the central computer package, to readmes, run system readme.txt, and I just copy and paste the commands into a terminal. Okay, as I already said, you copy and paste all commands from the run system readme.txt into your terminal in order to start up the system. This is like the rectification for both of the images for both slave robots, the SLAM algorithm on both robots, then the processing of the data, of the estimated data, like that means the filtering of the estimated data on the slave robots, on robot 1 and 2, and RVs in order to visualize the estimated data, the local maps and the global maps on the central computer. Then usually run the back files in a different terminal. But first, in RVs you have to specify the fixed frame in order to be able to visualize the point clouds. So you have to add point cloud topics which you want to visualize. Is point cloud 2. I already added them, so I don't show it here. Then you have to specify the topic name, the size of the point cloud, of the points, the decay time. I just set it to a big value, and the color and so on. So as I already said, I launch a bag files usually in a separate terminal because I have to stop and play them many times. And in the same terminal I run what you can see here is the LSD-SLAM algorithm, and the central computer I also run it in the same terminal as the bag files, but it's not necessary to do so. Now the system runs. Usually what you should do after or to run it properly, you should, before running the bag files, you should reset the LSD-SLAM algorithm by pressing R on the screen and reset RVis for a proper visualization. That's what I'm doing here. Then you can run the central computer and afterwards just run the bag files. That should be the procedure to properly run the system. Now it runs. You can see both robots, and that's the confusion matrix from FatMap, which states how likely it is that a robot visited already, or a place that another robot already visited before. Okay, now we'll see a full run of the system where the two robots move, and finally they will be at the same place and recognize that one will recognize that the other robot has visited this place already before. It will give a match for a FatMap match for the place recognition, and the central computer will calculate the transformation between the local maps of both robots in order to generate the global map. So as before, I reset the LSD-SLAM algorithm before running the system, then reset the RVis environment for a proper visualization. First run the central computer node and then the bag files, just an alternative to run the system live with cameras. Now the system is running, the robots are moving, and soon one robot will visit a place where which the other robot has visited before. Soon, that's now the place where they are at the same place. Now, one robot recognized that the other robot visited the same place before. I stop the program now, and I'll show you the images for which a match has been found. And you can see the SIFT feature points. I matched them, or the central computer matches the SIFT key points in order to calculate the transformation between the two local maps. So after running the system, the central computer calculates 3 point clouds, or creates 3 point clouds. One point cloud is the green one, it's a point cloud of robot 1, and robot 2, the point cloud of robot 2 is a red one. The red one is the point cloud of robot 2 in its local coordinate frame. And after the place recognition, or after the fat map detection, when the central computer calculates the transformation between both robots, it transforms the red point cloud into the coordinate in the coordinate system of robot 2 into the coordinate system of robot 1, and the resulting point cloud of robot 2, represented in the global coordinate system, which is the coordinate system of robot 1, is the pink point cloud. So just to show you a bit the point clouds, you can see the robot moved along the corridor, and the robot 2 moved around the corridor and turned left, whereas the robot 1, the green point cloud, came from the other side and turned right. And then they came to the same room, finally. Here you can see the corridor. It's in the academic building on the 5th floor, if you want to see it in life, of the Hong Kong University of Science and Technology. I try to zoom in a bit, just to show you how it looks there. It's the room. You can see after the filtering of the point cloud, it gets quite good. Before filtering, it's not that good. And the filtering is done on the slave robot. It's not done on the central computer. It also reduces the amount of bandwidth that is used to send the point clouds from the slave robots to the central computer. And in green, the point cloud of robot 1 came from the opposite side and then turned right. Together it's a bit messy, but you can see that it's at the same place, and that it works quite good. Like the rooms are overlapping. And as I already said, in red it's the same as the pink. The red and the pink one is the same point cloud, just transformed into another coordinate frame. And that's where that's the match, and with these both of these images, the transformation between the point clouds or the local coordinate system was calculated. Here you can see again that the pink and the red one is exactly the same, just transformed, represented in another coordinate frame, in the coordinate frame of robot 1, which is equivalent to the global coordinate frame. So, but note now that several things of the system do not work yet. At first, currently the system is implemented for 2 robots only. Then the calculation of the transformation of the matched images from 2 robots based on extracted SIFT key points does not work yet properly. Furthermore, I implemented a Kalman filter in order to estimate the differences in scale of the local maps. Every time a place recognition is detected between 2 different robots, SIFT key feature points are detected and matched. From the matched feature points and corresponding inverse depth values, the 3D world points are calculated. Note here that in general, the locations and hence the related pixels of the key points are totally independent from the pixels for which a depth value resulting from LSD-SLAM is available. However, I assume that for each key point the inverse depth value is known from LSD-SLAM. I justified this assumption by saying that both the key point extraction and the tracked points for the LSD-SLAM algorithm are based on the intensity gradient of the image and hence are in the same regions of the image. Furthermore, in the experiments it turned out that the estimation of scale is not robust or even wrong. It may be due to the fact that the assumption above is bad. However, it is also possible that the system and measurement model for the Kalman filter or the implementation of the Kalman filter is wrong. Finally, the iterative closest point algorithm ICP, which is used to refine the transformation between two robots, is implemented in the code but not used at the moment. This is due to the fact that the estimation of scale does not work. Hence the 2 point clouds are still quite different, the 2 point clouds from the two robots. But ICP needs a good initial guess because it is likely to settle down in a local minimum. Since the 2 point clouds are quite different due to differences in scale, it is impossible to give a good initial guess and hence ICP is useless.